Welcome everybody to our today's webinar. We are here right from our headquarter in Selb, Upper Franconia. We have a nice weather out there. We're sitting right next to our very famous porcelain manufacturer called Rosenthal. There we are coming from, and there is also the history of Netsch Gerätebau, Netsch analyzing and testing coming from. So from the very beginning, we started to think about how to optimize sintering processes, and this is our today's topic. We are discussing about how to optimize the sintering process of ceramics. First of all, I'd like to introduce myself a little bit. My name is Alexander Frenzel. I'm with Netsch since 2005. I'm married, I have 5 children, and I'm the business field manager for glass ceramics and building materials. Below there, you see my contact data and also my LinkedIn contact, so feel free to contact me there. There are some interesting other things about our company going on in this social media channel. So you're welcome to keep us in contact also on this channel. I also like to welcome my colleague, Dr. Elena Mukina. She's with Netsch since 2002. She's also married, has 1 child, and is a physicist in our research and development department. Also below you see her contact data. Elena will present you today our software tools that we have available for the optimization of sintering processes. But first of all, I'd like to remember you all who also attended maybe on our first webinar on this topic, where we discussed about sintering processes, as I talked about changing the game in process design of the ceramic sintering and debinding process. I like to remember that I talked about how to reduce R&D time, and we'd like to talk about how to reduce energy consumption, as well as reducing scrap, reducing numbers of test fires, and of course, finally, you will reach a faster time to market for your products. In summary, we like to talk about designing your process to the best. That's what I talked about in our first webinar of this series with the topic or the title, Speed Up Your Sintering Process. It's available for all of you who did not attend under the web address ta-netsch.com/the fastest way to design my sintering processes or design my sintering process. There is the address where you can listen to the last episode of this part of our webinar series, and it's all about this tiny sentence. It's all about the keyword conversion rate. How to optimize time in your sintering process. Yeah, you need to put an eye on the areas in your sintering process with the highest conversion rate, because this is the point in the process where maybe a damage like micro cracks or deformation can occur. Limit the maximum conversion rate to a certain level. Run as fast as possible where no conversion in your material takes place, and fasten heating rates where conversion is low. This is, yeah, the kind of main sentence what you need to keep in mind when we talk about sintering processes. The way how we get to the point to know where the point of the highest conversion or lowest conversion takes place is or are our methods for thermal analysis that we have available in our portfolio. On the left-handed side, you see an STA. This is a combination between a thermal balance and a differential scanning calorimeter. This gives you the information about weight loss during the burnout of the binder. In the middle of this picture, you see our dilatometers. Those instruments are able to give you information about the sintering shrinkage in the sintering process step. And on the right hand side, you see our light or laser flash equipment, which is able to give you information about the thermal conductivity during the process. All the data of these instruments are used for input in our Kinetics NEO software solution, which is able to simulate sintering and debinding processes. And now it's time to hand the microphone over to my colleague Elena. She will give you a nice insight into our software Kinetics NEO. So we changed the microphone.
Good morning, everybody. I am really happy to present you our Kinetic NEO software and to show online how we can make the optimization of the existing temperature profile. Optimization for what? Optimization in order to get a best quality in the shortest time. Best quality means no some cracks, no some caves, no some deformation, and it should be really as fast as possible in order to get the best results and to save the energy during your process. Let's see. Here, if we speak about sintering, then we have two parts. The first is debinding, and the second is the shrinkage. Debinding happens usually below 700 centigrade, and here we have some decomposition process. How to measure it? It's very easy. If we have decomposition of something, then the mass of the rest will decrease. So if we measure the mass during the heating, then we have some kind of curve, which called thermogravimetric curve, as the mass depends on the temperature. At the beginning, mass is 100%, and at the end, after decomposition, mass will be much below. Now, let's see what we have in our software. Here is real measured curve from 50 to almost 500 centigrades. It is done measurement with 3K per minute. It takes about a little bit more than 2 hours. It's more or less fast sintering or fast heating. The second measurement was done with YK per minute, 1K per minute. It means it will be much slower, about 6 hours. And the last one is 0.3K per minute. It's about 20 hours. Finally, we have 3 measurements, and these 3 measurements have decomposition or have debinding with very different intensity depending on the heating rate. The first one is very fast and very fast debinding. Second is green, slow heating, slow debinding, and the red is really very, very slow heating and very slow and less intensive debinding. If we switch to the temperature, then we see that all these 3 curves are not the same. For example, if we take about mass 96%, then for some heating rate, it happens at about 200 centigrade, and for another heating rate, it could be about 250 centigrade. Why? Because the heating rate is different and the process rate is different. Because the process rate depends on heating rate, depends on temperature, depends on time, depends on temperature profile. But what is the same? The same is the chemistry of the process, physics of the process. And now we can get information or extract information from this experimental data, and this information about a chemistry of the process which is independent on time and temperature. This information is the information like activation energy or pre-exponential factor or maybe order of reaction. So such things which are independent on time and temperature. Now we have activation energy, which is at the beginning of the process 100 kilojoule per mole, and at the end of the process is 250 kilojoule per mole. Pre-exponential factor is from 7 to 17, and now we can use this information to simulation. For simulation, we can use this kinetic information to get a simulation for 3K per minute, for 1K per minute, and for 0.3K per minute. So for the same heating rates which were done during our experiment. Let's see what happens. Here we have 3 curves. Points are simulated data, and the lines are our points are experimental data, and the lines are simulated data. For example, red simulated data for 0.3K per minute, green is for 1K per minute, and orange is for 3K per minute. Now we have 3 curves, simulated curves, which are everywhere in agreement with our experimental curves. It means that our kinetic parameters, or we say our kinetic model, can describe our process for any heating rate, for any temperature, and for any heating rate. It means that we can use our kinetic model for simulation for any temperature and for any heating rate. For example, for temperature profile, which happens inside your oven, during your sintering process. Let's see how to optimize our sintering process, our debonding process below 700 centigrade. Let's go to predictions or simulation. Here we have some non-optimized temperature program, which contains of several segments, heating isotherm again. And for all this data, we can calculate the mass loss and see what happens immediately. If you would like to change something here in this temperature program, then we can press calculate and see what happens for the changed temperature program. And now our topic or our task is to find a best quality in shortest time. Firstly, what means the best quality? Best quality means that we should have a good structure of material. For example, if we have debonding too fast, then the production of gases will be too fast, and the gases have no time to go out of our sample. And there are some bubbles inside the material, and these bubbles can have a high pressure and can damage the structure of material, and the quality of material will be not so good. Now, first point, we should find here in this temperature profile the time points where the debonding is too fast and where we lose the quality. We can change from mass loss to mass loss rate just to get a first derivative. And we can find here after 8 hours, the peak is the highest. Here we have about almost 0.5% per minute is the bonding rate. It means that exactly at this point we lose equality. If you would like to make equality better, then we must reduce the heating exactly at this time point and reduce the decomposition rate. How to do this? In segment from 100 to 150 to 200 centigrade, we reduce heating rate, for example, to 0.5 K per minute. Yeah, it's better. We make it slower, and now the composition is not so intensive, and we improve the quality exactly at this position. We reduce the composition rate 3 times. The next point is the next peak, or the next critical point is about 22 hours. Here we should decrease the heating rate again in order to improve the quality. We make it between 300 and 400 centigrade and decrease it, for example, to 0.5 K per minute. Now it's better. Now we have improved quality everywhere. The next part of our task is to make the time shorter as it was previously. Where we can make time shorter? At the points where reaction rate goes very, very slow. Then here, exactly at these points, we lose the time. For example, here at the beginning, first 2 hours, happens nothing. It means that here we can improve, we can make heating a little bit faster. For example, 1.5 K per minute. Now it is much better. Next one. Heating, okay. Isotherm at 150, okay. Heating from 150 to 200 centigrade is okay. Then isotherm at 200 centigrade. At the beginning of isotherm, the binding goes fast enough, but at the end, somewhere about 13 hours time point, the binding goes very slow. It means that this isothermal segment is too long, and we can reduce it because at the end of this isothermal segment happens almost nothing. Let's reduce it. The time from 4 hours to 2 hours. Let's see what happens. Yeah, it's much better. Now we can make the next peak a little bit less by reducing the heating rate. Yeah, it's better. Next one. We see that the isothermal segment at 300 centigrade is too long, and here the composition or debinding has very low heating rate. It means that this isothermal segment is not necessary. We can just remove it at all. Let's do it. Great. At the next heating segment, we can just a little bit reduce the heating rate in order to reduce the decomposition peak. For example, here 0.4 K per minute. Calculate. Next isothermal segment is not necessary because here happens nothing. Let's remove it. Next heating can be much faster because here the composition is too slow. Yeah, and the last isothermal segment is not necessary at all. Right. Now we have finally conversion rate reduced 3 times in regarding to the previous conversion rate, which was for non-optimized temperature program, and the time was reduced from 29 hours to 18 hours. I just switch to our presentation and see again non-optimized and optimized profiles. Non-optimized 29 hours and maximum reaction rate is 0.5% per minute. Optimized is about 40% less, only 18 hours, and maximal reaction rate is 3 times less than the original. Now we have optimized. The first time is debinding of the sintering process, which happens below 700 centigrade. Next part is sintering, is shrinkage above 700 centigrade. Here mass is not changed, but the length is changed because of shrinkage. We can measure length during the heating, and then we can get the temperature, the graphic of length on the temperature. At the beginning, there is a thermal expansion, then shrinkage, and then the thermal expansion of the product. And now we can optimize a second part above 700 centigrade. And this optimization is based on dilatometer curve. Let's switch to the temperature. Let's go to measurement profile. Here we have a measurement for sintering of aluminum oxide between 1150 to 1650 centigrade. It is done very fast with 30K per minute. It takes just only 16 minutes. Second measurement is with 10K per minute, and it takes 45 minutes. The last one is very fast. It's with 3K. No, it is slow with 3K per minute, and it takes about a little bit more than 2 hours. Now we have experimental data with 3 different heating rates. One is very fast heating and orange, and very fast sintering, very fast shrinkage. A second one is green, is slower heating, slower shrinkage. And the last one, red, is very slow heating rate and very slow sintering rate. If we switch to temperature, then again we see that the same length change happens at different temperature. Why? Because the heating rate was different, and kinetic of the process depends on time and temperature. And again, we can extract the value, the kinetic values, which are independent on time and temperature. And these values are activation energy, pre-exponential factor, and maybe order of reaction. Let's see here. For the dilatometer measurement, activation energy changed from 2,200 kilojoule per mole to 700 kilojoule per mole. Pre-exponential factor from 70 to 20. And now we can use this model for predictions with the same heating rate which were used during experiment, and see that the points are experimental data are in agreement with our feed data, with our simulated data for each heating rate. It means that we can use this model for predictions for any heating rate and for any temperature profile. Let's go to simulation. Here is non-optimized temperature profile for shrinkage. And now we should optimize it to get a best quality in the shortest time. What means best quality during the shrinkage? If the heating is too fast, heating rate is too high, then the shrinkage could be also too intensive. And if we have some temperature gradient, then the different parts of our material could have completely different shrinkage value, and therefore we have some mechanical stresses, and we can have some micro cracks inside material, and we lose equality. So if it is too fast, then we lose equality. If it is somewhere too slow, then we lose a time. And now we must optimize this temperature profile to reduce the intensity of a shrinkage at the points where it is too fast, and to make the time shorter at the points where we lose time. How to do this? We will switch from length change to length change rate in order to see where we have a critical point. The critical point is at 5 hours. After 5 hours from the beginning, here we have a shrinkage rate about 1% per minute. And exactly here we lose the quality of material, and exactly here we can get some mechanical stresses and some cracks. How to improve the quality? We should reduce the heating rate exactly at this time point in order to reduce the shrinkage rate at this time point. It is from 1250 up to 1300 centigrade, and we can reduce heating rate, for example, to 0.5 K per minute. Now we have reduced it from 1 to 0.35% per minute. The conversion rate reduced 3 times, and the mechanical stresses have reduced 3 times, and we have improved the quality of material. Next point, how to make it shorter. Now the temperature program, total temperature profile is about a little bit more than 25 hours. Let's make it shorter. First 4 hours happens nothing. Let's improve, make the heating faster. Great. Next heating, everything okay. The isothermal segment at 1300 centigrade is too long, and here the shrinkage almost not happens because the shrinkage rate is too low. It means that here we lose the time. Let's reduce this segment from 4 hours to maybe half an hour. Now it's better. Next one. Heating is okay. Isothermal segment at 1400. Here happens nothing. We don't need this segment. We can remove it too. Last heating is too slow. Here happens almost nothing. We must improve. We must increase the heating rate in order to make a reaction a little bit faster here. For example, 1.5 K per minute. Great. Last, isothermal heating is not necessary. Maybe we can remove 20 minutes from 3 hours. Yeah, and the last cooling is not necessary. So it belongs to the total oven properties, and therefore we will not remove it. Now we have a signal. Signal goes from 100% to 83%. Here is the length change. We have reduced a total length from 25 hours to 9 hours, and we have improved the quality of material. Again, to our presentation. Here we have left non-optimized temperature profile by 25 hours and 1% per minute for non-optimized value, and for optimized value we have 9 hours and only 0.4% per minute. We make the total process shorter, more than 60%. Now I would like to give the mic to my colleague, to Alex.
Okay, I'm back again. Yeah, hopefully this was an interesting presentation for you from Elena about our software. Thank you very much for that. So, as I said, Elena told you now, or showed you live in our software, how to find the points in your actual process based on the information from thermal analysis. Where are the critical points in your material during the debinding and during the sintering process? and where are the points where nothing is happening, where your process could be fastened. And those are the two things that you can get out of the software. Uh, where are the points to fasten your process, and where are the critical points which are reducing the quality of your outcoming products? So the thing that we discussed now during the live presentation was in principle the middle of this process. So where we talk about defining the firing process, there we have some helping instruments in our portfolio: the thermogravimetric analyzer, the dilatometer, and the LFA for thermoconductivity measurements. All those data can be used for optimizing your sintering process with Kinetics NEO, our simulation software. When we look in the process before, so in the process of preparation of raw material, our business unit grinding and dispersing has corresponding equipment which helps you to grind and to prepare your raw material, to grind and to mix it. And of course, also the particle size is an important input parameter which can help you to optimize the sintering process. So it is also possible to simulate the behavior of your sintering depending on the particle size of your raw material. So also this is an important factor for the quality of your products. When we talk about the other side of the process, the finished product, we are able to determine also dynamic mechanical properties on finished sintered parts, ceramic parts. This is a mechanical test procedure which is able to get properties like E modulus or Poisson ratio of your material. So in principle, the damping behavior of your material up to a temperature range of 1500 degrees C. Yeah, that's mainly it. What we can do in terms of your process, in terms of the specification of your process, and that, of course, helps you to speed up your firing process, to reduce energy consumption, to increase your product quality, to increase your productivity, and to speed up your time to market. So we hardly would recommend to simulate before doing the first test fire. Of course, if you have no own capacity for from your laboratory, you have no own laboratory, you have no own instruments to do all that studies, we are able to help you out with our laboratory services. So we also are able to do sintering process optimization as a service. Therefore, we provide a landing page, a website, ta-netch.com/sintering, where you are able to get in direct contact with our experts in our laboratories all over the world. In the end, I have a nice story where we can show that the process optimization with Kinetics NEO works. It's about a story from a standard refractory material. As you know, those are not that corrosion resistant at all, which is the reason why from time to time the lining of a process kiln needs to be replaced. From time to time, it needs to have a revision caused from corrosion from the process atmospheres, and our partners in that area is the company called Morgan Advanced Materials Haldenwanger, located in Waldkraiburg near Munich. They try to find a solution for the refractory materials field to develop ceramic foam which overcomes all that drawbacks of standard refractory materials. So this material is fiber free. You will have no contamination on fired articles in your furnace. It has a comparable thermal conductivity to standard refractories. It has a lower thermal expansion than refractories, and it has a high chemical inertia. It's a material which is based on alumina and fused silica, and it helps you to make the furnace lining of process furnace more resistant against the in-process stress, which is coming from on one hand side from thermal stress, and on the other hand side from in-process stress from in-process gases, outgassing of your fired articles, and so on. We did sintering process optimization on these materials, and we finished the optimization with a process which is now 60% faster than before, which helps them to get in a real good productivity range for the process of this material, Hall foam alumina. The picture here shows the uh, the deputy R&D director Mirko Lang in the middle on the left side, and on the right middle side this is Dr. Michael Rosumek. He is the R&D director of Morgan Advanced Materials Haldenwanger in Waldkraiburg, together with me and Elena during the Ceramitech show last year. Yeah, that's it for our webinar today. Thank you for your attention. And of course, you also have the possibility to get your demo version of our software today. Just visit our website, kinetics.natch.com. You can register to get your demo version, which is valid for 30 days. You can do some tests inside. We deliver also some examples with this demo version that you can play around. That's it for today. Hopefully it was a webinar which gives you a lot of nice and worthwhile information for your daily business. Thank you for attention. Have a nice day. Bye.